Let's talk about some definitions. First, we will start with extrema. That word is related to the word extremes, and basically it tells us high and low values. Now, there's two types of extrema. We can talk about local or relative extrema. Local and relative are used interchangeably. And then we have absolute or global extrema, which those words are also used interchangeably, just depending on where you hear them. So when we're talking about absolute or global maximums or minimums, those essentially are the highest or lowest points on the graph of a function. And when we're talking about local or relative extremas, those are essentially high or low points in little neighborhoods along the x-axis. So quickly, if I were to draw a graph, here's my y-axis, here's my x-axis. If I graphed something like this, and we were looking at the graph of this function between x equals a and x equals b, this here would be an absolute maximum. This here would be an absolute minimum. This point here would be a relative maximum, and this point here would be a relative minimum. So notice absolute means it's the absolute highest or lowest, and then relative maximums and minimums are relative to the neighborhoods or the areas around them. For relative maximums, I usually call these peaks, or I like to think of them as mountain peaks, and then relative minimums, we can think about them as valleys. All right, let's move on to the other definitions. We have increasing, decreasing, and constant. Those are pretty intuitive. We always want to remember when we're reading the graph of a function, we read from left to right on the x-axis. So if a function is going upwards as we go from left to right, then it is an increasing function. If it goes downwards from left to right, then it is a decreasing function. And then if it is a horizontal line, we think of it as a constant function. Example 15 says sketch a graph of the piecewise function f of x, then identify the domain and range. So we have f of x is equal to negative x plus 2 if negative 4 is less than or equal to x is less than negative 1. And then we have 3/4 x minus 4 if x is greater than or equal to 0. I'm going to start off with the second subfunction here. So we take on that subfunction if the x value we're looking at is positive or 0. So the way that we graph this is I know that this has a y-intercept of 0, negative 4. So I'm going to go ahead and plot that on my grid. So here is 0, negative 4. And then my slope is 3/4. That represents my rise over run. So I can go up 3 units, 1, 2, 3, and then right 4 units, 1, 2, 3, 4. And I can plot a point there. And then I'm going to go ahead and connect those with a line. All right, so I went ahead and I put a little arrow on my line indicating that it goes in that direction forever because our subdomain there is all positive numbers and 0. Let's go ahead and graph our next one. So I want to graph negative x plus 2 if x is between negative 4 and negative 1. Including negative 4, excluding negative 1. So I know that this would have a y-intercept of 0, 2. So I'm going to go ahead and plot that. And our slope is negative 1, meaning we would go down 1, right 1, or I could also go left 1, up 1. That would lead me here, here, here if I continue that slope pattern. Now, something that I have to take into account is my graph is only taking on that part when x is between negative 4 and negative 1. So I'm going to go ahead and erase this. And also at -1, there should be an open circle and then a closed circle at -4. I'm going to go ahead and erase that. And then I'm going to go ahead and connect these dots with a line. And notice that I'm not putting an arrow on either end of this line because, again, it only takes on that graph when x is greater than or equal to -4 and less than -1. So this is an open circle. This is a closed circle. And then here we have an arrow indicating that it's going on forever. So now let's go ahead and talk about our domain and range. So our domain, the lowest x value that we have is -4, and then that will go to -1, parentheses, because our domain does not include -1. Then we have union, bracket 0, infinity. And remember, infinity and negative infinity are always going to have parentheses on them in interval notation. So here is our function's domain, and then let's go ahead and talk about the range. Notice that the lowest y value on our graph is occurring right here, and that y value happens to be -4. And because there's a closed circle, that means I'm going to put a bracket on -4. Then what happens is this part of the graph goes up forever, meaning that I am going to attain every y value that is greater than -4. I don't even have to consider the y values on the other part of my graph because my blue line will go upwards forever and it'll actually already capture all of the y values that we will have in our range. So then our upper bound is infinity for our range. So there is our domain and our range. Now, the question doesn't ask for this, but let's quickly go over and talk about some extrema. So we can say there is an absolute maximum value of, oh, actually I meant absolute minimum, because if you notice, it goes off to infinity, so there's actually no absolute maximum. So there is an absolute minimum value of -4 at x equals 0. So that is where, when we're talking about the absolute minimum value, because here this is the absolute lowest point on our graph. Now, there is no absolute highest value because any y value that you give me, let's say you wanted a y value of 10, like somewhere here, I could give you an even higher y value that would fall on our graph. So there is no absolute, I'm going to abbreviate, so absolute max value of f of x. All right, and that concludes this example. Example 16 says use the graph of the curve below to answer the following questions. Part A says, does the graph depict a function? The way that we would answer this is we'd use the vertical line test, and any vertical line I draw is going to intersect the graph at most one location. So here, 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 here. This means that this curve passes the vertical line test and it does depict a function. So I'm going to write yes, it passes the vertical line test. Part B says identify any intercepts. So let's go ahead and talk about x-intercepts first. We have one here, we have one here, and we have one here. So our x-intercepts are -1, 0, 0, 0, and 1.5, 0. Our y-intercepts, if something depicts the graph of a function, that means that it could only have at most one y-intercept and not more than that, because otherwise it would not pass the vertical line test. And notice that we have our y-intercept at the origin, and the origin is the only ordered pair that could be both an x-intercept and a y-intercept. So that's what we have here. Part C says identify any zeros, and if you don't remember, a zero is an x value or input value that you plug into the equation that would make the output value 0, and it also happens that the zeros are the x-coordinates of the x-intercepts. So I'm going to go ahead and write this in set notation. So I have -1, 0, and 1.5, and these are our zeros. Let's go ahead and talk about the domain now for part D. Notice that this is a continuous function, and all that means is that if you draw your graph of your function, you don't need to pick up your pen or pencil to draw it in its completeness. And in other words, that means that there's no breaks when you're drawing the graph. So what that means is our domain is going to be a single interval, and it will go from -1.5 to 1.8, because those are the x values. The smallest x value is -1.5, and then the largest x value is 1.8. Part E asks for the range, so I'm going to fill that in here. First, we want to look at the highest y value, and that is here at 2.81, and then our lowest y value is here at -1.89. Remember, when you're using interval notation, the smaller value has to go on the left. So my smallest y value is -1.89, and it's a bracket since this is a closed circle, and then comma 2.81, that's also a bracket since this is a closed circle. I'm going to do some cleaning up of the screen. Part F says for what values of x is the function increasing? So f is increasing on the interval. So typically we use open intervals when we're talking about increasing and decreasing. So it's increasing wherever it's going up. So it's going up from here to here, and we need to look at the x values. So it's increasing from -0.56 to 0.89. And again, I'm going to use open intervals, meaning parentheses on my endpoints. So -0.56, comma 0.89. Then for part G, it says f is, for what values of x is the function decreasing? So we can write f is decreasing on the intervals. So now let's go ahead and highlight where they're decreasing. We're starting here, and then it's going down from there to there, but it's also going down from here to here. So I'm going to need two separate intervals combined with a union. So f is decreasing on the interval from -1.50 to -0.56 union 0.89 to 1.80. Part H says identify any extrema. So let's start with the absolutes. Here, this is the highest point that's available on my graph. So this would be an absolute maximum. Next, we have the lowest possible point on our graph, and that's happening right here. So this would be an absolute minimum. Then remember, I called relative maximums peaks and relative minimums valleys. So here I have a little mountain peak, and here I have a valley. So this would be a relative or local max, and this one would be a relative or local min. Remember, you can use relative and local interchangeably. Now, let's say you didn't have the graph that you could just label the extrema. How would we write this out in sentences? Here I've done that for you, and I'll go ahead and read them. So we can say f has an absolute max value of 2.81 at x equals -1.50. f has an absolute minimum value of negative 1.89 at x equals 1.80. F has a local max value of 1.28 at x equals 0.89. And finally, f has a local minimum value of negative 0.63 at x equals negative 0.56. So that's how you'd write out the extrema in sentences if you did not have a graph to label them. Example 17 says use the graph of the curve below to answer the following questions. Part A says, does the graph depict a function? It does because it passes the vertical line test. So I'm going to say yes, passes the vertical line test. Identify any intercepts in part B. Notice that there is an open circle right here, and so that means that our graph does not go through that point or ordered pair. This tells us that there are no intercepts. There are no x-intercepts and there are no y-intercepts. So I could write the word none. An alternative is we could use the empty set, which is a circle with a diagonal slash through it. And then C says identify any zeros. Again, there are none since we have no x-intercepts, or we could use the empty set again. Part D says what is the domain? Let's look at all the x values that are being utilized. Now, this is not a continuous function because in order to graph this, I could graph this portion, and then I would need to lift up my pen or pencil to continue graphing the next portion. There's a break, meaning that my domain is not going to be one single interval. So my domain starts at 0, but notice there's an open circle, so I need a parenthesis on 0. Then my x values continue to go until 4, because that's where this ordered pair stops. So it's going to be 0 to 4 with a bracket on 4, union, then my next x value that's being utilized is here at 6, and it goes from 6 to, and then stops at 10. Now there's an open circle when x equals 6, so I'm going to put a parenthesis on 6 and then a bracket on 10, and that's my domain. Now let's talk about the range. Notice that the y values on this line segment run from 5 to 9, but those are covered in all of the same those are covered within the y values that are on this part of the graph here. So I can ignore this and it will already be covered in that. And so in this part, we can say that the range is from the smallest y value is happening here at 0. Let me just highlight the y value, and then that goes up to the highest y value, which is 16. So I'm going to put a parenthesis on 0 and then comma 16, and I'm going to put a bracket on 16. So there is our range for this function. For part F, it says for what values of x is the function increasing, and we can say that the function's increasing. Notice that it's going up from here to here, and then it's also going up from here to here, and we're going to use open intervals, so it's increasing from 0 to 4 and also from 6 to 10. Part G says for what values of x is the function decreasing. We could again put the empty set, or we can write a sentence and say this function is never decreasing, because from reading from left to right, the graph is never going downwards. Now let's talk about any extrema in part H. So do we have an absolute lowest point on the graph? And the answer is actually no, because there's an open circle here. So if you gave me a y value like 0.1, I could always give you a smaller y value like 0.01. And because 0 is not included in the range, again, I can always end up giving you a smaller y value if you think you can give me the smallest possible y value. So for part H, there is no absolute minimum. And then there is an absolute maximum, and that's occurring right here. That is the highest possible point. So if I were to label that, I could say absolute max here. And then in a sentence, I could say, there is an absolute maximum value of 16 when or at x equals 4. And then next we want to talk about local or relative minimums and maximums. One thing to note about local or relative extrema is that local/relative extrema are never endpoints. So be careful about that, and I'm going to highlight on my graph. These are all endpoints, and so they do not have the ability to be a local maximum or a local minimum. So that's something important to know. Again, local/relative extrema are never endpoints. So for that reason, in this particular case, there are no relative extrema for this function. Let's move on to part I, which says create an equation for the graph. Now, it doesn't tell us what to call this function, so I'm going to go ahead and just call it f of x is equal to, and there's two portions to our graph, and so I'm going to have one part that takes on this subfunction if x is greater than 0 and less than or equal to 4, and then the other part is going to be if x is greater than 6 and less than or equal to 10. Let's figure out the linear portion of our graph. I'm going to go ahead and use my slope formula. So I'm going to call this x1, y1, x2, y2. So if I were figuring out the slope m is equal to y2 minus y1 over x2 minus x1, which is going to equal 9 minus 5 over 10 minus 6. And that is equal to 4 over 4, which is equal to 1. So if I were creating a linear equation for this line segment, it would be of the form y equals mx plus b, but we just found m, and we found the m value to be 1, so I can put 1x, or I could just put no number at all, because 1 times x is just x. And then how would we figure out the b value? Well, if this extended on, I know that it would cross the y-axis somewhere. How do we figure that value out? What we can do is we can replace x and y with some of these values. So I could use either of these ordered pairs. I'm going to use this bottom one. Even though it's not on our line segment, we're essentially just seeing if this extended on where it would cross the y-axis. So I'm going to go ahead and replace y with 6, and I'm going to replace x with 5, and then we have plus b. If I'm solving for b, then I'm going to subtract 5 from both sides, and I end up getting b is equal to 1. So that means that we have y is equal to x plus 1. So I'm going to go ahead and place x plus 1 here in my bottom row of my piecewise function. Now all I need to do is figure out what the other formula is. It's something where if I plug in 0, my output is 0. When I plug in 2, my output is 4. And when I plug in 4, my output is 16. If you see the pattern, the input is being squared or given an exponent of 2 to give us the output. That means that this is going to be x squared. And this is the final answer for part I, and this concludes this example. On this last page of this note packet for our section on functions and their graphs, here we have some graphs of common functions. In the first row, we have linear functions, which in general look like f of x or y equals mx plus c, where c is some constant. You might be more used to seeing it as y equals mx plus b. Either of those is fine. Here, this is a constant function. That's why it's a horizontal line. We talked about that earlier. Here we have the graph of y equals x, which is an increasing function. And then in the last scenario here, we have the graph of the absolute value function, y equals the absolute value of x, which looks like a V. Because remember, the absolute value makes all of the output values positive, so we don't have anything underneath the x-axis. Next, we have power functions, which are of the form f of x equals x to the nth power, where n is some natural number. So here we have y equals x squared, y equals x cubed, y equals x to the fourth, and y equals x to the fifth. These are some cases for, in the first case we have, this is an example of a quadratic. This is called a cubic. This is called a quartic function, and this is called a quintic function. So power functions, again, are of the form f of x equals x to the nth power, where n is some natural number. Then we move on to the root functions. Notice that a root function takes on the form f of x equals the nth root of x. And as we go through these cases, you'll notice that if the root n is an even number, then the domain has to be non-negative numbers. So that's specifically taking place when y equals the square root of x and y equals the fourth root of x, and in any case when the root is even, because we cannot take the eventh root of a negative number. And then lastly, we have what are called the reciprocal functions, where they take the form f of x equals 1 over x to the nth power, where again n is some natural number. And we have these various cases here, y equals 1 over x, y equals 1 over x squared, y equals 1 over x cubed, and y equals 1 over x to the fourth power. Now, these are all handy graphs to have in your tool belt, so please make sure that you memorize what these graphs look like. And really quickly, here are those graphs again. Thanks for watching.